Hello, everybody. We're going to work with 7.1 and 7.2 today. This is Tuesday, April 7th. Hopefully, everybody's well. New chapter. And this chapter is going to focus on working with rational expressions. But to be successful in chapter 7, we are going to have to import our ability to factor polynomials from chapter 6. And for that reason, it's wise to continue to strengthen that skill. What is a rational expression? First of all, a rational expression is basically when you have a polynomial over some sort of other polynomial. This is called a rational expression. And since a rational expression is a ratio of two polynomials, we have to be careful whenever we are dealing with ratios in mathematics. We need to ensure that we never perform a division by zero, because recall that when you try to divide by zero, you get an undefined quantity. So the first order of business we're going to tackle when working with rational expressions is to indicate what values of x will cause the rational expression to be undefined. And that's going to occur when the denominator is ever equal to 0. So the first couple of problems here, we're going to learn how to state any restrictions so that a rational expression is defined. So the rational expression is defined. All right, let's look at the first one here. Suppose we have this rational expression where we have 3x over x minus 6. So basically we have a monomial divided by a binomial. Now, our big concern is the denominator. We don't care about the numerator, whether it becomes 0 or not. It's always the denominator. If the denominator ever becomes 0 of any rational expression or fraction in general, the expression is undefined. So we need to focus on the denominator here. And so therefore, in order for this entire rational expression to be defined, we have to make sure that x minus 6 is never equal to 0. So therefore, x minus 6 can never be equal to 0. Because if the denominator x minus 6 is equal to 0, this whole rational expression will be undefined. Now, to find out precisely what numeric value will cause the denominator to be equal to 0, we would take this and solve it for x. Just pretend it's like an equation. We've got to get x all by itself. So we would add 6 to both sides. So therefore, we're finding out here that x cannot be equal to 6. If x is equal to 6, then look what happens to our rational expression. If I replace x with 6, we would have 18 divided by 0, which forces this rational expression to be undefined. So therefore, ladies and gentlemen, for this rational expression, 3x over x minus 6 to remain defined, for this expression to remain defined, x can never be equal to positive 6. So that would be the restriction you would have to place on this rational expression in order for it to remain defined, is you would have to say that x cannot ever be equal to x can never be equal to 6. Okay, so we're done with that one there. Let's try another one. How about x minus 1 over x times x minus 4? Here we have a rational expression where we have a polynomial over a polynomial. And our goal is to state any restrictions on x such that this rational expression will always be defined, or such that this rational expression will remain defined. Again, we focus on the denominator. We don't care about if the numerator becomes 0 or not. It's the denominator. If the denominator ever becomes 0, then the rational expression is undefined. So we have to make sure that this denominator never becomes 0. Well, notice this denominator is the product of two polynomials, x and x minus 4. So we have to make sure that each of these individual factors never become 0. So therefore, the restrictions placed on this rational expression so that it will remain defined is we have to make sure that this factor of x is not ever equal to 0. That's one restriction. And we have to make sure this factor of x minus 4 is never equal to 0. Well, we have to go a little bit further with the second restriction here. We have to actually solve for x here, and we do so by adding 4 to both sides. Therefore, another restriction is to say that x cannot be equal to 4. And there you have it, ladies and gentlemen. You have two restrictions placed on x. You have x cannot be equal to 0, and x cannot be equal to 4. So in order for this rational expression to remain defined, we have to make sure that x is never equal to 0 or x is never equal to 4. If x is 0 or if x is 4, then this denominator will become 0, and this whole rational expression would be undefined. So those are the restrictions for this one. Done with that one. Let's try another one here. All right, here's a rational expression, and our goal is to state any restrictions that have to be imposed on the denominator so that this rational expression will remain defined. And again, our only concern is that the denominator can never be equal to 0. So we take our denominator, which is this binomial, and we impose this restriction saying that the denominator can never be equal to 0. Notice, unlike the last problem, this denominator is not in factored form. So when your denominator is not in factored form, you have to take the entire denominator and set it not equal to 0, and then solve the resultant non-equation, if you will. I said non-equation because we have not equal to instead of equal to. Well, anyways, to solve this, we would have to try to now completely factor the left side of our situation here. And so we have to import our factoring skills from Chapter 6. After a little thought, notice there's nothing you can factor out of both these terms, but we do realize that we do have what's called the difference between two squares. 4x squared is the perfect square of 2x. 25 is a perfect square of 5. So we do have the difference of squares. So this left side can be factored immediately into the product of two conjugate binomials, namely 2x plus 5 multiplied by 2x minus 5. Now we have to make sure that none of these factors are ever equal to 0, because if they are, this whole thing will be equal to 0, which means our whole denominator will be 0, which means the whole rational expression will be undefined. So therefore, we got to make sure that 2x plus 5 is not equal to 0, and we have to make sure that 2x minus 5 is never equal to 0. Now we solve this one by getting x all by itself. We subtract 5 from both sides. In which case we'll have 2x is not equal to negative 5. Now we divide both sides by 2. And we get x cannot be equal to negative 5 halves. So that's one restriction placed on the rational expression here. Solving this one for x, getting x by itself, we add 5 to both sides first. Divide both sides by 2. And we get another restriction that says x can never be equal to positive 5 halves. And so there you have it, ladies and gentlemen. These are the two restrictions that must be imposed on this rational expression if it is to remain defined. If x is ever equal to negative 5 halves or positive 5 halves, this denominator would become 0, and this whole rational expression would become undefined. So this is just warming us up to our ability to identify any restrictions placed on the variable of a rational expression so as to force the rational expression to remain defined. This task will become more important when we start solving rational equations later on in Chapter 7, but Section 7.1 is just warming us up to that idea. The main thrust of this section, however, ladies and gentlemen, is learning how to reduce rational expressions. And reducing rational expressions, the first and most important thing that we need to do is we need to, first of all, make sure that both our numerator and our denominator are completely factored. All right, so let's just dive right in. Let's give ourselves a rational expression to play around with. How about negative 4 over 2x minus 8? And our goal is to completely reduce this rational expression. So to reduce this rational expression, we ask ourselves, can we factor the numerator and or the denominator? Well, the numerator, negative 4, is already factored. There's nothing you can do to factor negative 4, so we just bring it on along here. The denominator is 2x minus 8, but 2x minus 8 can be factored because we can factor out the greatest common factor of 2 out of both these terms here. And when we factor the 2 out, that leaves behind x minus 4.
Hello?
Now, ladies and gentlemen, what we're going to do is we're going to reduce this rational expression. Now that both the numerator and denominator are completely factored, we can see that the factor of 2 and negative 4 can reduce. So 2 divides on itself once, 2 divides into negative 4, negative 2 times. So this rational expression reduces down to negative 2 over x minus 4. We would say this rational expression is reduced. Okay, this is reduced. Here is a big caution. A lot of students, what they do when trying to reduce rational expressions is they fail to factor the numerator and denominator, and therefore they fail to reduce these things correctly. Ladies and gentlemen, if you have like a plus b over 2a plus, let's say, like 3b, if I gave you this rational expression and I wanted you to reduce this rational expression, temptation is going to have a lot of people say, well, I can reduce out the a's and I can reduce out the b's. That's called illegal mathematics. And the reason why you cannot reduce the a out with this a and the b out with this b is because these terms are not separated by multiplication, but they're separated by addition. Can't do this. You can't reduce the a out with the a, the b with the b. If you had a times b over 2a times 3b, then it would be legal to reduce the a's out and reduce the b's out. Reason being now is because these terms are separated by multiplications. So anytime terms are separated by additions or subtractions, you cannot reduce the things out between the numerator and denominator. Can't do it. So try not to fall into that trap there. In other words, back up here, I cannot further reduce the negative 2 out with the negative 4. Cannot do it because the 4 and x are separated by subtraction, not multiplication. So you must stop the problem here with this. And this would be, we say, the reduced form of what we started with over here. All right, so our instructions here are going to be saying reduce. All right, let's try this one here. We got a plus 4. And this one sits over a squared minus 16. Okay, again, it's illegal to reduce the a with the a squared, the 4 with the 16. The reason being is because these terms are not separated by multiplications, but they're separated by additions or subtractions. Now, in order to reduce this rational expression, you're going to have to try to completely factor the numerator and denominator first as polynomials. Notice the numerator a plus 4 cannot be factored in any way, shape, or form, so we just bring it on along. But the denominator, a squared minus 16, we realize is a binomial, and it happens to be the difference between what is called perfect squares. So a squared minus 16 can factor into the product of conjugate binomials, namely a plus 4 multiplied by a minus 4. Now that we have the numerator and denominator completely factored, it is legal to cancel out the entire binomial factors of a plus 4 here. The reason why we can do that is because separating the factor of a plus 4 and a minus 4 is multiplication. Because we have multiplication in between these binomials, it's legal to drop the a plus 4 out with this entire a plus 4. So our final answer, or reduced version of what we started with here, is going to be 1 over a minus 4. Hence, we have taken this rational expression and we have reduced it down to 1 over a minus 4. And we're done with that problem. Okay, let's try another one here. All right, here we have a rational expression. We want to completely reduce it. And so, again, try not to fall into the trap of doing things prematurely here. We cannot reduce the x out with this x or the 2 with the 10. Cannot do it. That's illegal. Reason being is because these terms are separated by subtractions, not multiplications. The only way we can reduce this or have any chance at reducing this rational expression is we first of all have to completely factor the numerator and denominators as polynomials. And this is where our Chapter 6 skills come back to visit us. In the numerator, notice there's a 5 that can be factored out of both these terms, and so we do that first. Factor the 5 out times, what do we leave behind? We'll leave behind x minus 2. Notice the denominator, x minus 2, cannot be factored in any way. It is not the difference between squares. 2 is not a perfect square, neither is x. So x minus 2 cannot be factored. Now that we have the numerator and denominator completely factored, it is now legal to reduce the factors of x minus 2 out. So x minus 2, we say, divides into this x minus 2 once, divides into this x minus 2 down here once. What we're going to be left with then, ladies and gentlemen, is 5 times 1, which is 5, and that sits over 1. When you cross this x minus 2 out, it's understood. You leave behind a factor of 1. Understood. So our final answer is 5 over 1, or we just say 5. So this rational expression reduces down to just 5. That one is done. Let's try another one here. Try to reduce 11a plus 33 over 6a plus 18. Again, try not to do silly, weird things. You cannot cancel the a's out here because separating the term of 11a and 33 is a plus sign. Separating the term 6a and 18 is plus. If it was 11a times 33 over 6a times 18, then you could cancel the a's out. But because we have addition here, you cannot drop these a's out, so don't do that. No, we have to ask ourselves, can the numerator be factored, this 11a plus 33? And after a little thought, we realize that we can factor the greatest common factor of 11 out of both these terms. So we factor 11 out, and that leaves behind a plus 3. The denominator has us factoring the greatest common factor of 6 out of both these terms here. There's the 6, times what would we leave behind? A plus 3. And now, ladies and gentlemen, now that both numerator and denominators are completely factored, it's legal to now reduce the binomial factors of a plus 3 out. And when we cancel the a plus 3's out, we leave behind factors of 1. The reason why we can cancel the a plus 3's out is because separating a plus 3's is multiplication, not addition or subtraction. So we're left with our final answer of 11 over 6, and that is the reduced form of this rational expression. That one is done. All right, onward we go. Let's try this one here. 7x squared minus 28 over 2x plus 4. We will try to reduce this rational expression. Again, don't try to do weird things like you cannot reduce the 4 into 28 out because separating 28 into 7x squared is subtraction. Separating the 4 into 2x is addition. You cannot do that. Can't reduce this x out with this x squared. No, we need to try to completely, first of all, factor all our numerator and denominator polynomials. Notice in the numerator here we can factor out a 7. Now, we're going to realize when we get deeper into chapter 7, oftentimes, we're going to have to do several steps until we arrive at the complete factorizations of a polynomial. And ladies and gentlemen, in doing the complete factorization in line with our main problem is going to have us rewriting these expressions over and over again till we get everything completely factored, and that's going to be tedious. So sometimes we may have to pick the polynomial up from our original problem, take it off to the side of our paper, and completely factor it. So you know what, this 7x squared minus 28, I'm going to pick it up, take it off to the side of my paper, and I'm going to completely factor it over here. When I get done factoring it completely over here, I'll bring it back and replace the numerator with its complete factored form here. So let's come back over here. Pretend we're back to chapter 6. We're being asked to completely factor 7x squared minus 28. And how can we do it? Well, the first thing we were taught is, can we factor anything out of each term of a polynomial? Well, notice we can factor a 7 out of each of these two terms, and that leaves behind x squared minus 4. We then realize upon further inspection that x squared minus 4, which is left behind, can itself be further factored down since it's the difference between squares. So x squared minus 4 further factors down, don't forget to bring your 7 down, into x minus 2 times x plus 2. Or you could have these switched around, x plus 2 times x minus 2. This then is the complete factorization of 7x squared minus 28. We bring this complete factorization back to our main problem and replace the numerator with it. Notice our denominator is only going to involve one step to completely factor it, so we don't necessarily have to take the 2x plus 4 and drag it off to the off to the side of the paper and take care of it. We should realize that we can factor a 2 out of both these terms, and we'll leave behind an x plus 2 in doing so. Now that the numerator and denominator are completely factored for this rational expression, it is now legal to drop out any like factors between the numerator and the denominator. And we see that the only factors that we can reduce out between the top and bottom would be the x plus 2's. Hence, when we drop the x plus 2 binomial factors out, we're going to be left with 7, x minus 2, and that'll just sit over just 2 times 1, or just 2. Notice we cannot further reduce the 7 and the 2, and ladies and gentlemen, this is it. This is your final answer. This is called the complete factorization of this rational expression we started with back over here. So the key you can see is we have to completely factor our numerator and denominators completely before we can do any sort of reducing. All right, here we have a rational expression where we have a trinomial over a trinomial, and we're going to try to reduce this completely. Again, do not fall into the errorful habit of canceling out the x squareds, the x's, reducing the 15 over the 6. That's illegal math, since these terms are all separated by additions or subtractions, not multiplications. So you cannot cancel the x squareds out. You cannot cancel the x's out. That's illegal. No, we got to ask ourselves, can we factor these trinomials completely in the numerator and denominator first? So we really have to go back to our chapter 6 skills. Fortunately, notice that both these trinomials are the easy type of trinomials to factor, since they're both trinomials with a leading coefficient of 1. To factor these, we discovered is pretty easy. If you want to take them off to the side of your paper and factor them, feel free to do so. And again, from what we learned in Chapter 6, we would use the product sum method for factoring this trinomial. We need two factors of positive 15 that sum up or add up to negative 8. And after a little thought, the only factors of positive 15 that add up to negative 8 would be negative 3 and negative 5. Those are the only factors of positive 15 that do indeed sum up to our middle coefficient of negative 8. So this trinomial in the numerator immediately factors into two binomials, namely x minus 3 times x minus 5. Let's come back up to our main problem and replace the numerator with its complete factored form, x minus 3 and x minus 5. The denominator factors in a similar way. Being a trinomial, one with a leading coefficient of 1, we're searching for two factors of negative 6 that add up or sum up to negative 1, the middle coefficient. After a little thought, we would stumble across the factors of negative 3 and positive 2 as being the only factors of negative 6 that add up or sum up to negative 1, the middle coefficient. Being the case, this trinomial immediately factors into the product of the binomials of x minus 3 times x plus 2. So both the numerator and denominator have been completely factored. Now that they're completely factored, it's time to see if we can reduce anything between the numerator and denominator. Notice the x minus 3 binomial factors reduce out between the top and the bottom. And so our final reduced answer for this rational expression would be 1 times x minus 5, or x minus 5, and that would sit over 1 times x plus 2, or x plus 2. And we're done. Please do not cancel these x's out in the end. You cannot do that because separating these terms is not multiplication but subtractions and additions. This is your final answer, reduced answer, for this rational expression back over here. So the key is, ladies and gentlemen, is first we have to completely factor, and then only after doing that can we even think about reducing. All right, let's try x cubed plus y cubed. And let's put that over x squared minus y squared and try to reduce this rational expression. The numerator. Can the numerator be factored? Well, after some thought, we realize that we have what is called the sum of perfect cubes. Being the case, ladies and gentlemen, this would factor, and you'd have to check back with your notes in Chapter 6. The sum of perfect cubes does factor. Do you remember how it factors? Well, recall, in general, if we have the sum of two cubes, it factors accordingly. So therefore, x cubed plus y cubed, following along with this pattern, where our a is really an x and our b is really a y, would factor as x plus y times x squared minus xy plus y squared. So that's the complete factorization of this numerator, the sum of two cubes. The denominator, we realize after some inspection, it is a binomial. It's the difference of squares, the difference of two squares. So this denominator would factor immediately into x plus y times x minus y. Now that both the numerator and denominator of this rational expression have been completely factored, we can see that we are legally able to reduce out the factors of x plus y. So those drop out, and our final reduced answer is going to be x squared minus xy plus y squared, and that will sit over x minus y. And we are done. This is the correct complete reduction of our rational expression we started with back over here. All right, one more here, ladies and gentlemen. We're going to try to reduce this rational expression here. Notice we do have a trinomial over a trinomial. It's illegal to drop these 5x squareds out. You cannot do that because separating these terms is not multiplication but additions. We have to try to factor these as trinomials. Unfortunately, they are the difficult types to factor because we have a leading coefficient that is not 1, and we cannot factor 5 out of all 3 terms. And so we're going to have to wrestle with factoring these the way we did back in Chapter 6 using the grouping method. All right, like I said, you might want to drag these trinomials off to the side of your paper and factor them completely, and then come back and replace the numerator and denominator with their factored form and then go from there. So here's what I'm going to do. I'm going to take these trinomials off to the side of my paper, and I'm going to try to factor them off to the side or maybe on a separate piece of paper here. So to factor the numerator here completely, first of all, we have to begin by the grouping method. We multiply the leading coefficient in the constant term, so 5 gets multiplied by -8. That becomes our product. So 5 times a -8 is a -40. And then we realize that we must have 2 factors of -40 that sum up of -40 that sum up to our middle coefficient of +18. Now we're searching for 2 factors of -40 that do indeed add up to +18. And after some thought, let's see here, -1 and 40, -2 and 20. These are 2 factors of -40, and notice that these are the ones that work because -2 plus 20 do indeed add up to +18, our middle coefficient. So these are the factors that are going to inevitably enable us to completely factor this trinomial. Now we rewrite this trinomial as a 4-term polynomial where the middle term, 18x, gets split up and rewritten as -2x plus 20x. -2x plus 20x are decided upon factors over here, minus the 8. Now we group together our first 2 terms by placing parentheses around them and our last 2 terms. Notice in grouping our last 2 terms together, we do not have to change the sign of the last term since we have a plus sign that precedes our 3rd term. Out of the first 2 terms, what can we factor out? We can factor out an x, and that leaves behind 5x minus 2. Plus, the last 2 terms, what can we factor out? Well, we can factor a 4 out of both terms, leaving behind 5x minus 2. Notice now that both terms, separated by addition, share a common binomial factor of 5x minus 2. So the whole binomial factor of 5x minus 2 can be factored out times, what do we leave behind in doing so? X plus 4. And that, ladies and gentlemen, is the complete factorization of this difficult trinomial here. Let's bring that complete factorization back to our main problem and replace our numerator with its complete factored form here. So 5x minus 2 times x plus 4. In a similar way, this trinomial in the denominator has to be factored using the grouping method. I'm going to let you do that, and when you get done, you will end up with a complete, accurate factorization of 5x minus 2 times x plus 3. All right, now that the numerator and denominator are completely factored, we're ready to reduce. Notice we can reduce out the binomial factors of 5x minus 2, and so our final answer for this problem is going to be x plus 4 over x plus 3. And that is the end of that problem. So this problem it took some time because we had to wrestle with factoring 2 difficult types of trinomials here. Ones where the leading coefficients are not 1, in which case we had to utilize what's called the grouping technique to take care of them. And so, ladies and gentlemen, this problem took a little extra time. We're going to discover, the deeper we go into Chapter 7, these problems are going to become longer and longer as the factorizations are going to bog us down. That's why it's very important to continue to strengthen your ability to factor polynomials from Chapter 6. I wish you all well. I am now going to sign off and get ready to compose the video for Section 7.2.